Oops, this is a version of the talks that I've given that's actually aimed pretty much at what I know to be the supergroup audience, who I think of as philosophical logicians primarily. So what I'm going to be talking about are logical systems that are tuned to natural language. So so I'm going to, at various places in the talk, I'll have a lot of historic remarks or remarks that are more conceptual, and at other places, rather more technical. So I think of logic as about inference in language, but it was, in a sense, hijacked to do the foundations of mathematics. And so what I'm trying to do is actually to return to the subject of logic for language, the way it would have been pre-Frege. And as a consequence of logic being developed with first order logic as the sort of top dog, the king system, there's a kind of a mismatch when we do it. So there's a kind of neglect of linguistic issues when we teach logic. And we also think about logic as being first order logic and primarily and nothing else. But from my point of view and a point of view that I'll try to suggest today, first order logic is too big and too small for what I want to do. So it's too big in the sense that it's undecidable. So I will have a kind of a methodological prejudice in favor of systems of logic that are decidable, which means that first order logic is sort of ruled out from the get-go. And at the same time, first order logic will be unable to capture a lot of the interesting things that I want to have something for logic to say, as I'll show you. Okay, so the program is to show that significant parts of inference in natural language can be done in decidable logical systems, to actually do all the work and to obtain axiomatizations of the whole thing so that we can understand it as logicians, to be completely mathematical and to connect it to everything in the mathematical logic tradition. Things like model theory, algebraic logic, complexity theory, decidable parts of first order logic, algebraic logic, things like that. To get things that actually run on computers. So I'm going to show you in the second half of the talk kind of work in the area of how we would use all this to do natural language inference on a computer. Okay, so this is a parallel studies of things that I actually won't be doing very much on today, but I could actually talk about them. And this is other versions of this talk would be about these things. So the history of logic, I mean, we could talk about people's reconstruction of the syllogistic logic. In terms of philosophy of language, I mean, there's a whole effort in terms of understanding model theoretic semantics and proof theoretic semantics. And what I'm doing here today certainly has something to say about that. And also about why we need variables whether we need variables and why we need variables and when they come up in doing logic. Cognitive science and models of human reasoning, well, for sure this is pertinent and relevant, but I won't have anything to say about it. In terms of linguistic semantics, this is totally relevant. So everything I'm doing is very relevant today for that, but I won't have much to say about it. I will have things to say toward the end about computational linguistics, since this is the actual smoking gun target of the whole thing. Okay. Here we go. This is the map of logical systems. So obviously, so each entry on the map is a logical system. So obviously, I'm not going to talk about all of them. I'm only going to talk about a few of them. And here are the kind of lines, border lines here. So the first border line I want to talk about is this line called Aristotle. So the line of Aristotle, below it are logical systems that are based on syllogistic logic with extensions. So syllogistic logic is down here. And the things above it are things that use extra devices that go beyond what you would do in syllogistic logic. You shouldn't think that just because I'm putting Aristotle at the bottom that it means that I have lower regard for it. Anybody who does the work that I'm doing will have a permanent, immediate and very deep debt to Aristotle for coming up with the logical world in the first place. This line of Peano and Frege has to do with the line of first order logic. So the systems that are to the right of that line are the systems that are sub-logics of first order logic. So I have first order logic at the top. Then I'm going to be actually very interested that there are syllogistic logics that are not on the first order side of the Peano-Frege border. So I want to show you what logic could be like if it existed on the other side of the Peano-Frege border too. This line of Church and Turing is the line that separates the decidable systems from the undecidable systems. And since I have, like I say, I have this prejudice in favor of things that are decidable, coming from computer science and cognitive science, I'm going to only talk about the systems that are actually below the Church-Turing boundary. So the one I'm going to talk about first is the logic A for all, and it's going to be the most simplest logic in the entire world. The only sentences in it are all P or Q. As you go up, you add more linguistic stuff. So the systems with S is the full syllogistic. The one with the greater than, that's on this side of the boundary, is adds cardinality kind of information. Like you could say there's more X than Y. The R has relations in it. So this is actually originally kind of thought about by De Morgan. The TR has and these are where you would get verbs, transitive verbs. The TR here has comparative adjectives like bigger than and smaller than, where you interpret them as transitive relations as well. The op has opposites like bigger and smaller and the relation between the two. All the ones with the dagger up here have a full negation on all of the nouns. So the thing about the dagger is how much negation they have. And I'm not going to really do much about these because it would take, actually each one of these is a full discussion by itself, or at least 10 minutes. So I'm only going to do it very quickly and get on with a lot of other stuff today. Okay, so this is the simplest logic in the world, I claim. So we start with a bunch of what are called nouns. This is unexplained nouns, P and Q and so on. And we make sentences of the form all P or Q. And that's the only syntax. I mean, it would be laughable as a syntax. And the model for this is just a set together with interpretations of the nouns as subsets. Now we have that, we have a semantics. We can define what it means for a sentence to be true or false in a model. And the interpretation of a sentence is just whether the interpretation of, it's true if and only if, the interpretation of the first noun is a subset of the interpretation of the second one. So so we have a, syntax and a semantics. And, like I teach this stuff. I have like a textbook on logic that starts with this, stuff like this. So, okay, here's an example. Here's a set, and here's a bunch of 3 nouns, and then you can see that the model either does or doesn't satisfy the various all relationships, just depending on whether, the meaning of the first noun is the subset of the meaning of the second one. And it's completely trivial. There is this kind of issue as to whether we want this to be done with existential import. That means like the way Aristotle did it, the way that if the meaning of a head noun is empty, we want to say that it's true. And of course, following the logical tradition, I'm going to say that it is true. But if you don't like this, I'm not like committed to that. You could actually redo everything, assuming the existential import, if that's what you want to do. So, we have the usual notions of semantics, and that is a model satisfies a set of sentences. And this capital gamma is going to be the set of sentences if it satisfies each one. And gamma has phi as a semantic consequence, just in case in the model theoretic sense, that is every model of all my assumptions is a model of the conclusion. So that's semantic. And then we can also do a proof system. So the proof system is based on the axiom all P or P and the medieval rule Barbara. So the medieval rule Barbara is the proof system, basically. And so we could talk about what it means to be a proof tree. So a proof tree is simply a tree in the usual sense, whose leaves are labeled with the assumptions. And we would write gamma proves phi. This is the proof theoretic notion. If there's a proof tree whose leaves are labeled with capital gamma and whose root is labeled phi. So for example, here's, oops, I think my keyboard is moving ahead of me. So here's a set of assumptions, all A or B, all Q or A, all B or D, blah, blah, blah. And here's a sentence phi, and we could see that this is a proof tree. So the 3 leaves are labeled in the set, capital gamma, and at each of the 2 interior points, we use Barbara. Right, all A or B and all B or D, we get all A or D. This is a use of Barbara. All Q or A, all A or D, we get another use of Barbara. And in fact, this is complete. So so I claim this is the simplest completeness theorem. And this is supposed to be a kind of a hint that all of the other proof systems that I'm going to have on the chart here are also complete as well. So, this is a very simple one. It can be done standing on one foot, as it were. So if suppose that this capital gamma has as a semantic consequence that all P or Q, will show that it could be actually proved. So we build a kind of canonical model of this, and we take as the points of the model to be the set of variables. So the variables are the points of the model, and they have a preorder, a natural proof theoretic preorder. So we define one to be less than the other if you could prove that all of the first are the second. And then we take the semantics. So now I'm going to make this set M into a real model by taking its semantics, the semantics of each noun to be the down set. So we interpret the noun U by the set of verbs V, such that you could prove that all V are U. And then we check that using the Barbara that it's that this is a pre-order, and in fact the model satisfies capital gamma. So this is a canonical model of gamma, and that means that since we assume that this is a semantic consequence, then in the model that we've built, it's actually true, which means that the meaning of P is a subset of the meaning of Q in that model. Since we have this axiom, all P are P, we can actually prove that. That means P belongs to the meaning of P. And since this is true in the model, that means P belongs to the meaning of Q. And I'm doing this quickly because you're all logicians, you all can actually do this. That means that P is actually less than Q in this pre-order, which is exactly what we want, that you could prove it from the axioms. This here is supposed to be a joke for everybody who grew up on cartoons the way I did. So, okay, so now this is just the first of the whole chart. So if we want to now add some, you know, like in the usual syllogistic, well, we add it to the syntax and we interpret it in the obvious way. Some P or Q just means that the intersection is non-empty of the meanings of the nouns. And then we have the logic extends in the obvious way too. We have the rule some P or Q implies, from that we can infer some Q or P. So this is the conversion rule for some in the traditional one. We get some P or Q semantic, you know, gives us some P or P. We need that one. And we get this rule, which is the medieval rule Dari. All Q or N and some P or Q, then we get some P or N. So this is the medieval Dari, and that's very nice. You can see here's an example of a proof tree. I'm sort of breezing through this quickly because I'm not going to prove the completeness here. These are like good exercises to do. When we add negation, so the way to add negation to this one way is to add set complement to the syntax. So we would add set complement to each of the nouns, where we force the model to interpret it, the complement of P by the set that is the complement of the meaning of P. And now the syntax, well, there's two flavors of syntax. There's going to be this S and this S dagger. So the S would have in it all P or Q, some P or Q, and you could add in it things like all P or not Q, which is another way to say no P or Q. And you could say some P or not Q. That would be, you know, you might say it more idiomatically as some P aren't Q. If you have that, that's the system S of usual, that's a nice system of syllogistic logic. If you added this one, which has more negation, you would get a somewhat more natural system logically, where you would have some non-P or non-Q. And of course, this is very unusual for somebody to say this, like some non-smoker is a non-drinker. But you can actually do both of these kind of logical systems, and here's what you would get. On top of the line, we would have the logic for all and some that I've showed. And on the bottom, we would get the laws of 0 and 1. So if all Q are not Q, all right, that means that there are no Qs. So that means, logically speaking, that all Q are P. So we would get that that's what's going to be a logic rule here. And if all non-Q are Q, that means that everything is a Q. So therefore all P are Q. We also get an antitone rule, which this is going to be prominent in later parts of this talk. If all P are not Q, that is, if no Qs are Ps, then it follows that, sorry, this one is no Ps are Qs, it follows that no Qs are Ps. Right? If so, no senators are alcoholics, then it follows that no alcoholics are senators. And we also get in this logic, well, if we have some P or P, that's a contradiction. So we would get ex falso in this logic. So that would be a logical rule. Now this ex falso is actually on this, when you do this kind of stuff, every little equivalence in the usual logic becomes an issue. So this is actually somewhat weaker than reductio in this logic. And in fact, you can actually show that this is a complete system. You don't need reductio. This is weaker and a slightly better rule than reductio. So you can, all this kind of stuff comes out, and it's all fairly easy to read and so on. And in fact, the completeness of this logic, I wanted to mention this because of all of the algebraic logicians who I think were in this supergroup. So the algebraic side of this is what are called orthoposets. So an orthoposet is a poset with a 0 and a complement operation that's antitone and involutive, and has a special feature that if X is less than both Y and its complement, then it's the 0. So this is kind of like the laws that we've seen. for set, inclusion, and complement. And in fact, the algebraic punchline is that Boolean algebra is to propositional logic what orthoposets are to the logic that I've showed before. And the completeness of the logic is tantamount to the representation theorem of the logic in the usual way we would do it with algebraic logic. Okay, so here's the map. So what I've showed is the A and the S and the S dagger. So I've showed these, and I want to show now, I should actually check what time it is just to make sure I'm in good shape here. Okay, so moving right along, let me do, so I want to go to show you logic beyond this border of Aristotle. So I'm going to make the case for the natural logic program that it can handle things that are not in the usual first order logic. And so the idea here is to take syllogistic logic and to extend it with things of interest that are not in the first order fragment. So I want to think about reasoning about quantities. So what are the simplest kind of reasoning about quantities? Well, I think they would be syllogistic logic plus sentences like this. There's at least as many x's as y's, more x's as y's, at most as many x's as y's, and so on. And then maybe most x or y. And so we can directly add those to syllogistic logic by, add them to the syntax and then interpret them just by cardinalities in the usual way, in just the way you would expect. So for things about at least as many and at most as many, you could kind of see what the thing would be. For most, it's of course controversial what most means. But just as a first cut, let's just say most means strict majority. So if I say most senators in the United States voted for a bill, that would mean 50% plus one. That's what most means for this. Now, if you object to this, you would get a different logic. That's great. So I'm not committed to this being the meaning of most. What I'm committed to is the idea that we decide on a meaning and formulate the semantics and do the proof theory and get the completeness theorem. That's basically what I want to do here. So this would be the rules. So when you do this kind of stuff, you get a lot of rules, I'm sorry to say. So the rules that are on the top are kind of ones we've seen. As you go to the bottom, you get more and more obscure and arcane rules. So I want to talk about the ones in red. Let's see what I can say here. So I want to talk about this one here and these ones here. The bottom ones are the two ex falso rules. So we've already seen, like, if some P or Q and no P or Q, that's a contradiction. And we also get another contradiction by saying if there's more P than Q and there's at least as many Q as P, that would be a contradiction. So that's another way to get a contradiction in this system. So this system is actually complete. And let me tell you what the rules that I've got here are. So this one here is complete, and it actually depends on the fact that I only want to interpret this on finite sets. So if I tell you that all farmers are carpenters, and that there's at least as many farmers as carpenters, at least, and they're finite sets, then actually the carpenters and the farmers are the same sets. So they have to be the same interpretation. So you in fact would get all carpenters are farmers. So this depends on the finiteness of the logic. Now it used to be that every time I would give this talk, somebody would at the end raise their hand and say, well, what about the infinite sets? So finally I had to do it. So I did it with Selçuk Topal, who wanted to do this, and you can change the logic to do it on infinite sets, and about half of the rules go away and are replaced by other rules, but it can be done. Okay, this one here, the majority run, oops, sorry, this one called half. Okay, so a lot of the action in the completeness theorem has to do with half and half. So if I tell you that there's at least as many smokers as non-smokers in the room, that means that the smokers are half or more. And if I tell you that there's at least as many non-drinkers as drinkers, that means that the drinkers are half or less. Then it follows, since there's only one room and it only has one size, there has to be at least as many smokers as drinkers. So that's a rule about half. The top one says there's a half or more are smokers and half or less are drinkers. So that means the smokers have to be at least as many as the drinkers. This one here, the majority rule, it has 3 premises. I'll let you read this. It actually is valid. I mean, it's a sound rule rather, and it takes some thinking to think about it. You can prove that actually the system can't be axiomatized with rules that only have two premises. So you actually need this very complicated rule. After seeing it, I kind of wonder if any human has ever used this rule in doing reasoning about sizes, but could be done, and it is sound, and you need it to get the completeness of this thing. Now, here's what Quine said. So this is for the philosophical logicians. So Quine said, if we ever were to devise a logic of ordinary language for direct uses on sentences as they come, we'd have to complicate our rules of inference in sundry unilluminating ways. So one has to wonder how Quine would know this. And of course, this, are these unilluminating? Are they sundry? Of course, they're slightly unilluminating. Some of them are kind of repetitive and unilluminating. But I actually think that once you play with this, these are sort of illuminating. I mean, you get to something about half. This is the logic of these things. And in fact, one thing you can do with this logic is it's not only complete and decidable, it's actually in polynomial time. So to the extent that human beings are working with the logical stuff of the form, there's at least as many x's as y's. You don't have to move to second order logic. You don't have to move to anything undecidable or even NP complete. This is actually does a certain amount of what humans do with this stuff. And so, I said before, you can all object to this. If you want to object to my whole program on the grounds of Quine, you certainly can, because I'm definitely up for the criticism that a lot of this is sundry and unilluminating. In fact, this one has been implemented. I don't think I want to show it to you, but it's on this CoCalc. You can type in like a bunch of assumptions like I've got here. This is harder than a person could ever understand. All non-A or B, blah, 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 and then a conclusion. And it would actually, well, in this case, it tells you that the conclusion doesn't follow. And not only does it tell you that, it gives you a counter example. So that's the nicer part of this, is the proof search, in fact, gives you the counter model if it fails, canonically. It gives it to you pretty canonically. Well, it doesn't give you the smallest possible one. We don't know how to do that, but it gives you a nice counter example, and that's it takes no time at all, right? In other cases, it gives you a proof. So if it says all non-x's are x and some non-y are z, it could prove that there's more x than y by using the logic rules, and the rule that does the work at the very bottom is the rule called more. So this would be the proof, and you can do this and teach this to people and stuff like that. Okay. So you can also do it with the word most. So the word most is fairly complicated. If I had a whole talk here, I would actually invite you to think of what you think the rules are for most. So here's some rules for most. I don't think I want to tell you what these are. There are rules for most. In fact, for most, you actually need an infinite batch of rules that I have at the bottom that generalize the observation that the middle here, if most z are x and most z are y, it follows, right? If they're at least 50%, then by the pigeonhole principle, some z have to be y, right? They have to have an overlap. If they're at least 50%, if they're strictly majorities, then if the z is a strict majority over x, if a majority of z's are x and a majority of z are y, then the x and the y have to overlap. And in fact, this is the first of an infinite batch. The second one would be this one. It actually has 10 premises. And I would be, again, very surprised if any person ever used this for anything. But it is a sound rule, and you need it for the completeness theorem. And it's a regular set, and you can do all this. It could be implemented when we haven't really done this. Okay, so this is it. I mean, you need infinitely many axioms. It's in polynomial time, et cetera. Okay, so now I want to think about relative clause. So this is my favorite thing to do. So if you're awake and watching me, what do you think about this? So this is my favorite thing, is to ask the logicians. Supposing I tell you that all skunks are mammals. So that's our assumption. Does it follow or not that all who respect all skunks, fear all who respect all mammals? Okay, so if you understand this, let's see who thinks so. If you think it follows, raise your hand. If you think it doesn't follow, you can tell me it doesn't. Nobody's doing this. Or maybe I'm going too fast here. Maybe I've seen this thing already. Okay, this is my favorite thing. Or nobody's showing me whether they think it follows.
We have to figure out how to raise our hands.
Just raise your hand. I see your pictures.
Oh, that one.
Just raise your
All
hand.
right.
Just raise your hand. I see your picture. If you think it follows, you could raise one, and if you think it's not, you could put your thumb down.
There we go.
Shay thinks it follows. Okay, I see a few more people. Okay, so it follows, and let me show you why. Okay, so if all skunks are mammals, then all who respect all mammals respect all skunks, and notice that they have switched. That's antitone. So that means if that antitone means you've switched something. And therefore you can do it again, because if the red and blue switch, then everybody who fears all of the red guys now has to fear all of the blue ones because you've switched it twice. So it follows by using the principle of antitone twice. Now we do it with logic. So this is term logic, in the term logic tradition, kind of done for the 21st century. So now we start with nouns and verbs. So before we just had nouns, and the verbs, they contribute to make terms. So a term is a verb, all, another term. So the terms are a recursive construct, and the sentences that we have are just all between two terms. So you don't have to really read this, you could really look at the example. So the terms are things like dogs and cats and ants and birds, and then you could put a verb in front. So you could say see all dogs. So that would be a good term. You could say respect all who see all dogs. So the who is not part of the syntax. It could be, but the who is how you would read it in English. You could say something like love all who, respect all who see all dogs. So you could actually now make the kind of sentences that we just had with the skunks and mammals. And you would read these in English with relative clauses. The semantics, well, you interpret verbs as relations on a universe, just as you would in usual logic. The verbs are interpreted as relations, and then the interpretation of the terms is just exactly what you would think it would be. These are set forming operators. So in addition to the dog set, you would get the see all dog set, etc. And the rules are, well, we have the axiom and Barbara, since we're sort of committed to those from before, and then we have the anti-rule. If all y's are x, then all who love all the x's love all the y's. And again, they've switched. And that's the rule. And then, now you could do it. Now this is now a logical deduction in this system. If all, from all skunks or mammals in one step, you get all love all mammals, love all skunks, right? This is the first anti-rule. And then in one step, you get all hate all, love all skunks, hate all, love all mammals. And you could keep going with that. Okay. Let's see what time it is here. Okay, so. Okay, so I don't think I want to show you the, so these are the logics like this R star down here and so on. The logics that are up here that have more negation are provably not syllogistic. So that means, so this is an interesting thing for logic. So you could prove that they actually can't be axiomatized by finitely many sound syllogistic rules. So they need something else. And what they need is variables. So I don't want to do this, but you can kind of add variables to the syllogistic in a nice controlled way. So you don't add it in and explode into first order logic, but you have variables and you can prove the completeness theorem. So I'm not going to do this. This is kind of what I believe that Fitch did something similar in Fitch's paper, Natural Deduction Rules for English. So please excuse this example. Let me use the example as John is a man, any woman is a mystery to any man. And then Jane is a kind of temporary variable, which you assume to be a woman, and you do this kind of stuff. And the interesting thing from my point of view is that Fitch knew that there was something special about this word any, that sometimes it means all, and sometimes it means every, and he was trying to get the word any correct. So I've gone back and fixed Fitch. So I basically looked at Fitch and try to see what he did fits into this program. He actually did this without a semantics. So he did this in '73, the same year that Montague started to publish. But he did it without the semantics. He just did it as a kind of proof theoretic thing. We could talk about this later. So here's my review. So we've seen some of these logical systems There's computational complexity. I mean, if you were into it, as you get more and more linguistic stuff, you get more and more complexity. So the bottom one's, you know, in log space, and then there's in CoNP by results in the AI tradition, various theorems that I proved, and more than other people have proved, about logics that are like this in this system. We also know about the finite model property. So the finite model property, for most of the logic that I've talked about today, actually all of them, have the finite model property. So they do it by kind of filtration on top of the Henkin construction. Filtration from modal logic, because these systems have a modal kind of flavor. And you can get things low down that don't have the finite model property, and things that don't have the finite model property kind of go up in the chart. Okay, so that's about it for this. Now, okay, I actually want to give up on this because I really would like to, I really think that most of what humans do in their reasoning is going to be very close to the bottom here. These ones that are in here are kind of interesting for us, for logicians, but they're very unusual for people to actually use the resources of negation in a kind of way with all of the rest of this that actually people would use. So I really am interested in the fact that actually computers can do logical inference on naturally occurring text as well as people can for the first time in history. So I think that's like an important thing for logic. And I would like the logical tradition to have something to say to this, which actually it doesn't at the point. So in fact, a neural learner, a neural net learner does better on all this than a person. It does better than the logical tradition. And it doesn't use anything of the logical tradition beyond the fact that it was sort of constructed on a Turing machine and stuff like that. So all the stuff that I'm doing now is of no real interest. Well, maybe you could ask me about this later, to actually how a computer would do the inference. So I would like to do that. And now I would like to actually, so now just take a step back and in a way kind of throw away all the stuff that I did so far to show you something else. So what does follow from mean in this? So follow from means that a sentence follows from a list of other sentences should mean something like, whenever we accept the assumptions, we should accept the conclusion. And it should be human level kind of acceptance. And so here's one way to formulate this for logicians. So what we would do is we would take a situation, so everything would have to be situated because the meanings of the words are depending on a context in such a strong kind of way. So we would take a situation and we would axiomatize what's true there with another set. And we would then kind of like ask whether our assumptions and this other background set implied what we're interested in or not. And this notion of implication would be in some logical system. And if this didn't happen, if it was a deviation, well, maybe this would be a kind of performance issue, or maybe people ran out of processing memory, or maybe we didn't have our good assumptions or stuff like that. So that would be kind of how do you formulate this. Now, I think of this as like the holy grail for a lot of different fields. So, but everybody, in order to make progress on this, has to give up something. So if you're doing linguistic semantics, which is where a lot of this sort of comes from, I think you give up on inference. Because in a linguistic semantics, they almost never look at what actually is the theory of inference. If they had asked about the theory of inference, they would have done all the results about all and stuff like that, you know, as soon as they had semantics. But in fact, nobody actually thought about that in the world of linguistic semantics. From the good old-fashioned AI, well, you give up on human competence because you actually do it in the logical tradition, but you don't care that it's in a decidable system, and you don't care whether people could actually do it. From natural language inference, which I guess is the target of a lot of my thinking these days, you give up on being explainable because you just want a neural net to do it, and you don't care how it did it or what the explanation post facto is. If you're doing psychology, you basically just look at the syllogistic logic and stop there. So everybody has to give up on something to do what they want to do. My feeling is what I'm going to do is I'm going to give up on, I'm going to give up on statements in an artificial language. So I would like to, so what I did in the first part of the talk is I give up on real language. So now what I want to do is to give up on formal languages and use parsed input instead of that. So I want to give up on the idea that our sentences come from something that we have pre-parsed in some pre-given way, like those trivial languages that I had a half an hour ago. So I would like to maybe subject everybody to a small video. So here's my, I made a video that kind of explains the ideas that I'm going to explain. And so this is just 3 minutes and I hope you can all hear it. So I did this once. So this is absolutely for people on the street. This is a video, was a video for a contest about, can you explain math ideas without symbols, without any symbols for an educated person on the street. So here goes. It's just 3 minutes. So.
Words that you don't know.
Sorry, let's start again.
How can you answer a question involving words that you don't know? How can a computer do it? We'll how, and we'll see how math enters in. Here's a sentence with some made-up words.
All the glogglfish swifferate past a yub.
And now let's ask.
Do all striped glogglfish swim past a yub?
To answer, let's take an ocean voyage to meet a big glogglfish. Some big glogglfish are striped. We put all this information in a scale. Up means more general, and down means more specific. They swim and they swifferate. Here is the scale of the verbs move, swim, and swifferate. Supposing I tell you about a picture that
all the glogglfish swim.
What would you be committed to? Here are the sentences that you would accept. These are what you infer from my statement. The pattern is, on the left, we move down the scale. On the right, we move up. When we change the word
all
to
some,
the pattern changes. And when we use the word
no,
the inference is different yet again. It's down both times. And when we start to look at other sentences and other words, we see the same kind of patterns all over the place. The same happens with numbers. Let's look for a second at 41 minus 32. The arrows tell us that to make 41 minus 32 bigger, we can either move 41 up or 32 down. Let's put numbers and language together. In mathematics, we put things which are similar under the same conceptual roof in order to study them together. That roof is called a preorder. It's what we are calling a scale. We think of a sentence like, all big glogglfish swim, to be the all function applied to a noun and a verb input. The language of preorders allows us to talk about increasing and decreasing functions. Let's go back and answer the question that we posed at the beginning. What you do and what a computer could do can be studied as an application of mathematics to everyday language.
Okay, let me quit on this. Oops. This always happens here. Okay, so I have like 15 minutes here. Let me do this. I want to do this one quickly. So, come on. Too much open here. Let's just. Yeah. Yes, if anybody wants to ask me any questions while I get this back here, you can. Yeah, okay, so I have to do this quickly. So here's the idea. I would like to show how this idea of finding these arrows and doing replacement can be used to do kind of real world inference. So we would start with a sentence like, every cat that Fido chased ran. And we don't want to think about that as coming from some kind of grammatical thing. We want to think about it as given to us along with this parse tree that's given by a combinatorial categorical grammar parser. So I choose this CCG because it's the system that both has a running implementation that does reasonably well and a syntax semantics interface that's connected to functions and mathematics, so in a way that I can sort of understand and work with. So of course the grammar has various kind of issues. For one thing, it's massively ambiguous, and the CCG parser has to give you what it thinks of as the most likely or the best parse. So it's even touchy, and there's, you know, for people who are into that, you should ask me about what we do to actually make sure that this works out. And the way that this works is you start with a lexicon. So that means what is going on at the leaves of the tree are various statements about various syntactic categories. So that's the second column here. And then there's general rules about how you build the tree that's given by the 6 CCG rules. Actually, there's a few others that almost never get used. So these are function application rules. This is raising, Montague raising, and this is function composition. And then you basically build your tree. So you look for a tree that uses those 6 rules at the inside leaves, and you would like it to end up with a sentence at the bottom. And that's what parsing means in CCG. Now, there's a syntax semantics interface that's going to be important. So it goes like this. You start with entities and truth values, and I'm going to take numbers as well because I want to think about quantity information. And you formulate higher order semantic types. So this is like the function set as you would do it in the typed lambda calculus. And you would translate the syntactic types into the semantic types. And what goes as a model here, so this is a model in the Montague sense, is that you start with an arbitrary set to be your interpretation of the E for entities. And then you would take function sets, like this is the full function space, as you go up the typing information. And your words has to be interpreted in the appropriate semantic space. Of course, a word like every and some, the logic kind of words like determiners, have to be interpreted in a special way. So you can interpret the nouns any way you like, but you can't mess with the interpretation of like all and some and who and stuff like that. And then the CCG rules, the 6 rules that I had there, are actually like function application, function composition, and type raising. So, so now what I want to do instead is to think about these arrows like I had in the video. So to think about the arrows, we have to change everything about the categorical grammar to go from sets to pre-orders. So instead of going from 2 sets to the function space, we actually would go to 3 sets. The monotone functions, so now we have pre-orders. So we can talk about the monotone functions and the antitone functions, that is the ones that go reverse the order, and all functions, the ones that sort of don't care about the order. And so instead of having function sets, we have 3 kinds of pre-ordered function sets. And so I mean, I think you all know about pre-orders, since pre-order is just a set with a reflexive and transitive relation. And with the pre-order, you know, you can make new pre-orders. So one way is to take a pre-order and another set, and to take the pointwise monotone, to take actually the set of all functions. That's now a pre-order with the natural ordering on it, the pointwise order. Of course, the truth values is a nice pre-order, and when I do that, I mean, you do it in the natural way with false being less than true. And then you could take a pre-order and you can turn it upside down. You could flatten it, which means throw away the order. You could take products. Okay, you could do all this kind of stuff. So here's an example. I mean, this is the usual Boolean. This is the opposite. This is the flat one. You take various products, and all this kind of stuff is needed in what I'm doing. And then we have the definition of monotone. So a monotone function from one pre-order to the other is one that respects the order, and an antitone function is one that inverts the order. And so all the concepts that I've done today, like even back to the skunk and mammal example, are kind of about this stuff. And so doing what I'm doing now kind of puts it in center stage. So like negation is antitone, stuff like this. I don't think I want to do all this. So what you want to do now is to take everything that we do in usual semantics and do a pre-ordered version of it. So the type for NPs in usual Montague grammar is E to T. So it's something that maps a noun to a truth value. That's what a noun phrase would be. And it now splits into 3, depending on whether this is a plus or a minus or a dot on this arrow here. For this one here, e to t, well, e is always interpreted as a flat preorder. And the functions from a flat preorder into any preorder, well, the flatness means that we don't care about the order. So the monotone functions, every function is automatically monotone and antitone and so on. And then instead of, so now we know that the noun phrase splits, and in fact, all of our determiners, which is where a lot of the logic kind of stuff goes on, now have to have dedicated meanings of very special types. So every would be from n to np plus, where it's going minus here and plus on the next one. So that's the special point about every, as being down in its first argument and up in its second. And so now we now have these special kind of types, and I think the idea for doing something like this goes back to David Dowdy's paper around in the early 90s. And so now, instead of we have the same syntactic categories we had before, but basically we now enrich our semantics by putting in inferential information in here. So now we put in the pluses and the minuses and the dot into the semantic types. And so now what that means is we can and we actually do this with the rules. So the rules of grammar, in addition to the 3 rules of the CCG that we had before, we get 3 more rules, which are fairly complicated. And I don't have time to talk about them at all. So I'm not going to tell you what these mean, but it's kind of a fairly interesting technical point having to do with the kind of adjunction between sets and complete Boolean orders as what it comes to mathematically, especially this rule called K. And what you do is now you start with a syntax tree. So this is what the parser gives you: some dog chased no cat. And now you say, well, look, I really would prefer the semantic types, which are the ones down here, to be the ones that have these arrows in them, or the plus and the minus. So you now do all this, and you come up with an algorithm that takes the tree on top and puts in the pluses and the arrows like this. So that means that you now have an algorithm and something that can be implemented because it's done on top of a parser. So the parser gives you stuff on the top, and your algorithm enriches it to have in it the arrows and the pluses and the minus. And there's a soundness theorem that basically says that if you're if you interpret the words on the leaves the right way, especially the determiner kind of words, and if the tree matches the 9 rules of the grammar, and if the root has a sentence with an up arrow, then assuming that, then actually the arrows here do what you want them to do. That is, they license replacement as a form of inference in any model. So that's a kind of soundness theorem for the whole thing. So with that, and so the tricky part of all this is actually coming up with this algorithm and implementing it, and well, actually coming up with it and proving that it's correct is kind of an interesting exercise. This was done with my PhD student, Hai Hu. If you click on this link, you would actually find the GitHub for the whole thing. So you can download it and run it. And so here's examples of this. So you could type these sentences into the whole thing, and it would come up with these as its output. So you type in "no frog walks," and it returns that with the arrows here. So that means that if no frog walks, you now know that no spotted frog walks. And so you can go from frog down to spotted frog, or walks down to walks quickly, and stuff like that. And so all these arrows here are sites of inference, just like they were in the video. And now, so you can now try to see, well, what can we do with this? So in 5 minutes, I'll try to tell you. So this is a famous kind of data set in this area called the fracas. So you might have something like a schoolgirl with a black bag is on a crowded train. And you want to know, does it follow or does it contradict? Or is it neutral to no schoolgirl is on a crowded train? And of course, this one here should contradict. Whereas this one, a schoolgirl with a black bag is on a crowded train, does it follow that a girl is on a train? Yeah, it follows. So you should be able to do all this, and you should be able to get a computer to do all this. So the way that it would work is you would have these arrows on your sentences, and you would have a kind of database of things that you believe or you know or you temporarily assume, like dogs are animals, which maybe you know from WordNet, or you learned it in school or something like that, or cats are animals or whatever. And you might even have ones that are like right in some situations and wrong in another. So in our town, there was a scooter last year that descended here called a bird, and everybody knew that a bird was a scooter. and stuff like that. And you have various kind of things about verbs and facts about adverbs like this, hit vigorously is less than hit, stuff like that. And you have logic stuff that you can depend on. So you know that 1 is less than 2, 2 is less than 3, 3 is less than 4, most is less than some. So you have all this even at the level of the higher types. And then you do logic by replacing. So you see whether, you know, what counts as inference is, can you replace respecting the arrows? And so the system is called monologue. And we tried running this. And so since I only have a minute, I knew this was running out of time. So, well, how does it actually do compared to other systems? So actually replacement on the arrow does okay. It's only okay, but it's okay. It does a certain amount of interesting inference. You don't have to translate things to first order logic. In fact, you can't really translate things to first order logic, but it does a certain amount of inference. If you want to do better, you should add a few rules on top. So those rules are things like the fact that determiners are conservative functions from semantics, or the fact that most adjectives are subsective, things from linguistics, Boolean operations, you know, how the and the or work. You actually should actually allow things like passivization and numerous kind of transformation sentences. Now, if you do that, well, in fact, you could also add the natural logic rules from earlier. So you might as well start with syllogistic logic, since it's a good logical system. If you do that, then monologue turns out to be roughly as good as other kinds of logic systems that I'll mention in a minute. They're not as good as the best in neural net learners. But we kind of went on to show that if you take a neural net learner, which does better than what we can do, and you add artificial data that's produced by our system running it backwards, that is, you can do inference backwards to generate inferences, then use those for training data for the neural net learner. It would slightly improve them. So logic can help out the neural net learner. So let me mention, there's a lot of other work that's logic-based natural language inference work. So one of them is from Lasha Abzianidze, who based it on Tableau. So his system is basically a massive Tableau logic prover. Hitomi Inaka looked at the translation of CCG into higher order logic, so directly translating from the same root that we do, the CCG, and translated it into higher order logic, and then called CoCalc as a theorem prover to do that. And Katerina Kaluli and her collaborators worked on a system called graphical knowledge representation, which takes dependency parse, and roughly speaking, and from a different kind of tradition of linguistic syntax, and came up with graphical things, and then incorporated this into a logic system. In fact, all of these are basically PhD dissertations from Lasha's was earlier, and these ones are fairly recent or ongoing. And they all do kind of about the same level, even though they're based on different ideas, interestingly enough to me. So here's a kind of comparison with machine learning. So a natural logic base, like the ones that I'm talking about, actually do things at very high precision. So if they say something is an inference, usually it comes with a proof. Unlike the machine learning one, which can do it, but they have no proof whatsoever. It just happens to be right 89% of the time. The logic-based ones usually have a hard time on syntactic variation. So you can't apply a logic rule unless it's in a certain form, and so you're stuck at various places that you're not stuck in machine learning. But you have a very good explanation of what's going on, and that's lacking in these ones. Okay, so I need to finish up here to let people ask questions. So let me just say what I did in the second part of the talk is I've showed that you can extend categorical grammar monotonicity, which was an idea due to von Bentham, to the CCG setting. I showed you we actually have a running system called monologue. You can actually polarize the sentences that, like I showed on the video. You can incorporate that into an actual running system, something that actually works, you know, to see whether something implies. You can generate data that will help a neural net learner learn. And there's other interesting logic systems in the same neck of the woods. So once again, here's my what I'm trying to do with natural logic in a bigger sense. I want to show that parts of what people do in inference can be captured in logical systems that are decidable, and to look at the axiomatizations, to connect to all the math fields that we do connect to in logic, and to get running systems that actually work. So this is kind of the high level discussion of natural logic. So here's my last words for the logic audience. So first of all, as a result of doing a lot of thinking about inference and actually being part of a group that studies this carefully, I'm not sure that I understand it. So I'm sure that there's more to it than just does it follow for the person. So there's probably a whole lot more to say about what a human being is doing when they're doing inference than maybe the psychological world will help us to understand. We should ask whether a complete proof system is a semantics. So we should try to see whether having a complete logical system, complete, you know, in the semantic sense, means that we could throw away the ladder of semantics and just use the proof system to be the semantics. We should do logic beyond traditional logic. We should actually connect to all the kind of mathematical fields like database theory, all the fields of computer science that are doing things in logic that are logics that are weaker than first order logic. They're doing interesting things. I found that there's a lot to learn from making running systems. So that I kind of highly recommend this to us. So here's my historical influences. I mean, everybody doing this knows that Aristotle is the one that we're most indebted to. In the categorical tradition, in addition to the people here, I mean, I'm mainly interested in, influenced by Steedman, who came up with CCG and got it to work, and von Bentham, who had the insight that the categorical grammar syntax semantics interface could be merged with monotonicity information to do something like the monotonicity calculus. And in fact, what I did was basically to take von Bentham's work and adapt it to CCG, because CCG is the only way to get a system that runs. In terms of syllogistic logic, there's a lot of people who, some of them I think might even be here, who did work on extended syllogistic logics. I did the most with Ian Pratt Hartman and learned a lot from him and other people. In terms of semantics and proof theory and people doing that, well, I mean, many of you may know Summers' work and Engelbretson. I mean, it's sort of in the same, it's in the same ballpark of using a monotonicity kind of calculi and things like that. Von Bentham work directly related, and David Dowdy. I have done the most work on that I didn't describe at all on lambda calculi with monotonicity with Thomas Eichard. You might want to look at alternatives to the whole thing, like Hanoch Ben Yami's work, or Peter Ludlow and Zivanovich's book that do natural logic, you know, inspired kind of work, but it's actually not the same as what I'm doing in a different way. Although they're not interested in the computational kind of aspects the way I am. In terms of the computational work, well, I kind of mentioned all of these people. I mean, Valeria Depayeva has numerous kind of important work over the years in thinking about what inferences and how it's related to computer science and logic. And these people here are all doing important ongoing kinds of work these are all young people doing all this important stuff. So these are all the people that I've learned so much from and have been privileged to work with over the years, and want to thank at all times. And just mention now that doing natural logic, like in this talk, I mean, allows us to do both a very classical subject in logic. I mean, this is Aristotle and Leibniz, and I think of what we're doing is very much in the footsteps of them. And at the same time, this is the computer that beats the human at jeopardy without using any of the work from the logical tradition, really. It allows us to sort of connect this very old work, some of the most classical work in the whole Western society, to this, which is some of the most interesting and important and cutting edge work in Western society, or all of society. And so doing natural logic allows us to sort of bridge the gap and to think about both of these together. So that's my